So we're going to move on and look at strain states, since we're going to cover the more circles in lab. Now, strain states are shown in table 4.2, page 74 of your book. This is in section 4.9. And you can have something where the volume is constant. So, for example, in image A, the block that that white cube compresses into the blue plane, or like it looks kind of like a piece of plywood. In B, the cube compresses into a long brick shape. So in directions Z and Y, there is compression. In direction X, there's extension. So the E value, elongation, in X is greater than in Y and Z. Because in X it's positive, Y and Z it's negative, but in Y and Z they're equal to each other. The first one, the elongation in the X direction, is the greatest, because that's where it's now longest. Elongation in Y direction was second largest, because it's still positive, but it's less than X direction. And elongation in Z is the smallest, it's negative. Case C, elongation in Z is negative. It's compressing. In the X and Y directions, it's equal. It's elongating positively, it's getting longer, but equal amounts in the X and Y directions. Another condition, there's no change in the Y direction. The X direction is positive, it's elongating. The Z direction, it's negative, it's compressing. What these are telling us about is the orientation of the stress that's causing all of this. By seeing how much and in what direction the elongation is happening, we can know something about where the largest stress was, where the smallest stress was. This is useful. This tells us about plate tectonics, for example. This tells us what to look for elsewhere. If we know the stress fields, we can figure out things about fractures and fracture networks. Incredibly useful in petroleum engineering and in geothermal industry work. Now, that is all for constant volume. Sometimes we have volume change as well as elongation. For example, this case E, there is no change in the Y direction or the X direction. So elongation is 1. In the Z direction, elongation is negative. Or the minor correction here, elongation is less than 1. It's not negative. We go back to the equation for elongation. Okay, I'll edit that again. Okay, I know this is starting to get really long, guys. Almost done. Section 4.10, representing strain. The orientation and magnitude need to be expressed. We can use a two-dimensional strain ratio for simplicity. Focus on 2 dimensions. The third dimension, of course, exists in real life, but we just worry about 2 at a time. And so then we can look at a strain ellipse. We find a projection plane close to the principal plane of stress. So, you think about a cross section. Well, if we want a useful strain ellipse, take a cross section that's actually going through the principal direction of stress. And then we can have 2 ways to show the strain. We can draw the shape of the sectional ellipse on the surface, and we can show this orientation of the strain axes using plunge and direction of the plunge. So the orientations, we've got these different marks on a map showing us orientation. These are actually ellipses. It's really hard to see because of the pixelation. It looks kind of like jagged lines, but they're very compressed ellipses showing the orientation of the stress. So where it's compressed, where it's narrow, there's a lot of stress. Where it's elongated, where it's wide, there's low stress. Down in the right-hand corner, we've got strain ellipses. Strain ellipse just shows us which way the rock is elongating, which way the rock is compressing. So we can map the stress or we can map the strain. A Flynn diagram is showing us a chart or a graph-based image, and the slope is the amount of constriction or flattening. So if you look, all of these are extending in the z direction, but in the top left here, it's compressing a lot in the x and the y, and an equal amount. In the center, it's compressing in the x direction, and stationary in the y direction, and extending in the z. In the bottom right, extending in the y and the z direction equally, and compressing in the x direction. So the plot here is taking where the y-axis is the maximum stretch divided by the medium stretch. So you know how you can calculate the elongation for x, y, and z directions. And stretch is actually another term we'll see in lab on how to calculate stretch. Super easy. And then the x-axis is the plot of the intermediate stretch divided by the minimum stretch. So we have x over y is the vertical axis, and y over z is the horizontal axis. And this gives us a plot where our data point could be somewhere in here, anywhere in here, but exactly where it shows up gives us an idea of what's going on. We could plot 4 data points or 400 data points and have, or 4,000 data points, and have like basically a data cloud in there, and where all those data points were falling, where they're more concentrated, where they're less concentrated, tells us a lot about the stress and the strain in that whole area that we're getting all the data from. A Ramsey diagram, on the other hand, is for plotting incremental strain. We're not going to actually do this, but this is something that you might see. The vertical axis is the log of x over y direction, and the horizontal axis is the log of y over z direction. These you'll see a lot in publications. These kind of things tell you about that same plot, but in a graphical representation, telling you basically, you can see where they fall on the plot because they're all numbered, and it tells you about the strain. It's just more elaborate than a simple strain ellipse because it gives you a sense of the 3D strain that's going on. It takes a lot of practice to look at one of these and know, hey, this has shortening in the x and lengthening in the y and no change in the z, or it takes practice. It's good to have a chart like this. Lets you know, hey, okay, when it looks kind of like this, it falls here on the plot. That means this, because you have the explanation of the plot. Okay, now I know what's going on. So having a reference for these is really useful because these get used a lot. So how are we going to know what's going on? I talked about, hey, there's a concretion or there's a fossil, there's something that got squished. But does everything distort the same? No, of course not. So we have to be careful. We have two types of strain markers, things that we can look at to figure out what happened. Passive and active. Now, if we have a rock and there's something included in it, that inclusion might be similar composition, might be very different composition, might be more rigid, might be less rigid. If we have a block of clay or Play-Doh or something, and we have a marble inside of it, a glass marble, that marble is a lot more rigid than the clay. We can start pushing down on that clay, and the clay will squish all over the place. The marble's unchanged. Or we could put, a little balloon filled with water, pack our clay around it, and start pressing on the clay. That balloon filled with water squishes more easily than the clay does. Or we could stick a piece of red clay in the middle of blue clay. It's the same stiffness, it's just a different color, so it's still a marker, but it's going to deform exactly the same as all of the rest. Everything's going to deform evenly. So a passive marker is something that is similar in strength. The red clay in the middle of the blue clay. Passive marker, it's deforming at the same rate. An active marker deforms at a different rate. It could be faster, it could be slower, but basically it's active. It's doing it at a different speed than the background. If we compare markers that have a known original shape, it can help us solve for the finite strain. It can help us solve for what the total change to the rock was. Sometimes it's useful to look at both passive and active, plus what's passive in one material in one bed might be active in another bed if you have alternating beds. So you want to look at everything. If, for example, you have a sandstone bed and a shale bed and another sandstone bed, do you know, did all three beds get compressed because there was a huge amount of stress applied, or did only the sandstone beds deform due to a lower amount of stress being applied? If they're all still horizontal and flat, how would you know? Well, first, how would you know there was any stress, or strain rather? Well, you would look for strain markers. If there were little shale pieces, shale's not a real good example because you don't get circular spherical shale concretions, but imagine you could, just for this example because I already started it. And there were some circular shale concretions or concretions with the same strength as shale in the sandstone. And then there were some sandstone concretions which do form. I actually have a nice, beautifully, perfectly spherical one sitting on my shelf right above me here. And there's some of those. If we look at those markers in the sandstone bed, and we see that these sandstone concretions have compressed into ellipses. Hey, there's strain. We know that these beds have been compressed. We look at those shale-like concretions, and we notice that they either haven't compressed or hardly at all. So we now know that the shale bed has hardly compressed at all. They weren't in the shale bed. They were in a different bed with lower strength, or at least for compression, and therefore they were active markers, but they told us about a nearby bed. So both pass